Welcome back. Let's practice using the triple scalar product. All right, so here's our first example. We have for vector v, vector u, and vector w, find the triple scalar product involving those three vectors. And that triple scalar product looks like this, where we take the cross product of vector u and vector w, and then multiply that by vector v via the dot product. All right. So vector u cross vector w is going to give us another vector, right? The cross product always gives you another vector, and so then you take that vector and multiply it by vector v via the dot product. Now we're going to use a little shortcut method to do both the cross product and the dot product at the same time, but in general that's what this notation is telling you, that you are taking the dot product of vector v and the result of this cross product. Now, for the vectors that we're using in this problem, we have vector v, which is the position vector of the point 2, 0, 1. We have vector u, which is the position vector of the point -1, 3, -2. And then we have vector w, which is the position vector of the point 1, -1, 2. And so if we want to calculate the triple scalar product of these three vectors in this way, what we can do is set up a 3 by 3 matrix. And so here's what that looks like. We're going to take vector v dot the cross product of vector u and vector w, and that will be equal to the determinant of a 3 by 3 matrix composed of the components of these three vectors. In particular, the first row will be the components of vector v, the second row will be the components of vector u, and the third row will be the components of vector w. All right, the components of these vectors need to be placed in that particular order in order to calculate this specific triple scalar product. All right, the first vector's components go in the first row, the second vector's components go in the second row, and the third vector's components go in the third row. All right, so let's fill those in. The components of vector v are 2, 0, 1, so we will have 2, 0, and 1. The second row will be the components of vector u, which are -1, 3, -2. So we will have -1, 3, -2. And then the last row will be the components of vector w, which are 1, -1, and 2. So we have 1, -1, and 2. All right, so now that we have this 3 by 3 matrix set up, all we have to do to calculate the triple scalar product is find the determinant of this 3 by 3 matrix. And the process is very similar to how we calculate a cross product, right? This is very similar to how we set up the cross product of two vectors. The only difference is that the first row no longer has our standard unit vectors I, j, and k. Instead, we replace them with the components of vector v, the vector that we're dot producting, if that's a word, with this cross product. All right, whatever vector you were multiplying by that cross product via the dot product, that vector's components need to be in that first row. Okay, but other than that, if you are familiar with the process of finding the cross product of two vectors, then finding the triple scalar product is not too bad. And if you're not familiar with that process, be sure to check out my lesson video on the cross product where you can learn more about that. Okay, but let's get started here. In order to calculate the determinant of this 3 by 3 matrix, and as a result, the triple scalar product, you want to start by looking at the values in the first row, that being 2, 0, and 1. We'll start by looking at 2, and we're going to cross out the row and the column that 2 is in, and then use the remaining 4 values to calculate a 2 by 2 determinant that will then be multiplied by 2. All right, so we're going to be multiplying 3 by 2 and then subtracting -2 times the -1. So let's do that. This will be equal to 3 times 2, which is 6, minus a -2 times the -1, which is +2. So we have 6 minus 2. And then we're multiplying by 2 the value which we covered up to find that 2 by 2 determinant, right? We covered up 2, that first value in that first row, and so that's what we will multiply by that 2 by 2 determinant. Now, following the definition of a 3 by 3 determinant, we subtract the next term, which we get by looking at 0, the second value in that first row. We cross out the row and the column that 0 is in, and then use the remaining 4 values to calculate a 2 by 2 determinant. So we'll have -1 times 2, which is -2, minus -2 times 1, which is also -2. So we will have -2 minus -2, and that will be multiplied by 0, that value in the first row that we covered up in order to find this 2 by 2 determinant. All right, now that's just going to make this whole term 0. So if you wanted to, you could just cross this out and write 0. But I'll worry about simplifying in our next step. And before we get there, we have to do another term here. We need to add our last term, which we will find by looking at 1, the last value in that first row. We'll cross out the row and the column that 1 is in, and then use the remaining 4 values to calculate a 2 by 2 determinant. We'll multiply -1 by -1, which is +1, and subtract 3 times 1, which is 3. So we'll have 1 minus 3, and that will be multiplied by 1. That value that we covered up to find our 2 by 2 determinant here. Okay, so hopefully you were able to follow that process. Like I said earlier, it's very similar to how you calculate a traditional cross product, except instead of multiplying each of those 2 by 2 determinants by the standard unit vectors I, j, and k, we're multiplying by those components of vector v that are in the first row instead. Okay, but now if we simplify what we have here, 6 minus 2 is 4 times 2 is 8, so this is equal to 8 minus 0, right? We already said that this whole term will be 0 because we're multiplying by 0 and anything times 0 is 0. So I'll just make a note of that. This will become 0. But then we're adding all of this to 1 minus 3 times 1, and 1 minus 3 is -2 times 1 is still -2. So we will have minus 2. Okay? And so now if we simplify, 8 minus 0 is 8, and then minus 2 is 6. So this is equal to 6. 6 would be the value of the triple scalar product. Okay, let's take a look at another example. All right, so next up we have for vector A equal to I plus 2j plus 3k, vector B, which is equal to 4i plus 5j plus 6k, and vector C, which is equal to 7i plus 8j plus 9k, find the triple scalar product of vector A multiplied via the dot product by the cross product of vector B and vector C. Okay, so this is very similar to our previous example, except we are working with 3 different vectors. So the process is exactly the same. We're going to be setting up a 3 by 3 matrix that we then calculate the determinant of to find this triple scalar product, okay? But it's important that you set up that 3 by 3 matrix correctly based on the order of the vectors in this triple scalar product. Notice that we have vector A, then vector B, and then vector C. So we'll have the components of A in the first row of that matrix, the components of B in the second row of that matrix, and then the components of C in the last row. All right, so let's set this up. We are going to be calculating the triple scalar product of vector A dot the cross product of vector B and vector C. And this is going to be equal to the determinant of a 3 by 3 matrix that we are going to set up now. The first row will be the components of vector A, which will be the coefficients of I, j, and k, right? These vectors are given to us in standard unit vector notation, rather than just the regular vector notation that our vectors were in the previous example. So determining the components is a little bit different, but hopefully by now you're used to it. The components of I, j, and k for vector A are 1, 2, and 3. So we'll have 1, 2, and 3. Then the second row are the components of vector B, and the coefficients of I, j, and k are 4, 5, and 6. And so we'll have 4, 5, and 6. And then finally, the last row will be the components of vector C, which are the coefficients of I, j, and k, and they are 7, 8, and 9. So we will have 7, 8, and 9. Okay, and so now all we have to do to find the triple scalar product is calculate the determinant of this 3 by 3 matrix. And so let's do that. Let's start by looking at our first row here. In particular, we're going to be looking at 1 to begin. We'll cross out the row and the column that 1 is in, and then use the remaining 4 values to calculate a 2 by 2 determinant that we will then multiply by 1. And so we'll have 5 times 9, which is 45, minus 6 times 8, which is 48. So we have 45 minus 48, and that will be multiplied by 1, that number that we crossed out to find those 4 values. All right, then we're going to be subtracting that second term. You always subtract the second one. That's just the definition of how we calculate a 3 by 3 determinant. Now we're going to be looking at 2, the second number in that first row. And so we're going to cross out the row and the column that 2 is in and use the remaining 4 values to calculate another 2 by 2 determinant. So this time we will have 4 times 9, which is 36, minus 6 times 7, which is 42. So we have 36 minus 42, and that will be multiplied by 2. That number that we covered up to find those 4 values that we used to calculate this determinant. And now finally, we will add our last term, which we will find by looking at 3, the last value in that first row. We'll cover up the row and the column that 3 is in, and use the remaining 4 values to calculate another 2 by 2 determinant. So we will have 4 times 8, which is 32, minus 5 times 7, which is 35. So we will have 32 minus 35, and then we're multiplying by 3, right? We covered up 3 right here to find those 4 values, and so we multiplied the determinant of those 4 values by 3. Okay, and so now if we simplify, 45 minus 48 is negative 3 times 1 is still negative 3, so this is equal to negative 3 minus 36 minus 42, which is negative 6 times 2, which is negative 12. So we'll have minus negative 12, and then we were adding that to 32 minus 35, which is negative 3 times 3, which is negative 9. So we are adding negative 9. All right, and then if we simplify further, negative 3 minus negative 12 will be the same as negative 3 plus 12, right? Those two negatives will cancel out. So negative 3 plus 12 is positive 9, and then we have 9 plus negative 9, right? This will become 9 plus negative 9, which will just be equal to 0. So the triple scalar product of these 3 vectors, A, B, and C, in this order is equal to 0, which is a pretty interesting result. I talked about this a little bit in my lesson video on this topic, but when you find that the triple scalar product of 3 vectors is 0, what that means is that those 3 vectors lie in the same plane. They are coplanar, okay? And so all that means is that if we were to look at a plane in 3D space, let's say it looks like that, all 3 of these vectors, A, B, and C, would be contained within that plane. So maybe this is vector A, maybe this is vector C, and maybe this is vector B. It doesn't really matter where they are within that plane, but the point is none of them are pointing out of the plane in this direction or backwards out of that plane or pointing this way or this way or this way. They're all within that plane. We don't know what that plane is without doing some extra work, and we're not interested in determining that here, but the point is that when the triple scalar product is 0, that is what's happening. These 3 vectors are all in the same plane. They are coplanar. And the reason we know that is because, as you'll see with the next couple examples, the triple scalar product can also be used to calculate the volume of a 3D solid known as a parallelepiped. And so if the triple scalar product represents the volume of some solid, and we find that it's 0, then that solid doesn't have any volume. We're working with a 2D shape instead, which doesn't have volume because it's 2D, meaning that all 3 vectors are in a flat 2D plane. There is no depth or third dimension to that shape formed by the 3 vectors. Okay, but with that, now let's move into our next example, which I sort of already alluded to, where we will use the triple scalar product to calculate volume. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the video and take a look at the next example. All right, so here's our next example. We want to use the triple scalar product to find the volume of the parallelepiped having adjacent edges defined by these vectors. Vector v is equal to I plus j, vector u is equal to j plus k, and vector w is equal to I plus k. Okay, so this example is a little bit different than our previous 2 examples, but we're still calculating a triple scalar product of 3 vectors. It's just that we're looking a little bit more into what that triple scalar product actually represents. All right, we can use the triple scalar product to find the volume of a parallelepiped. And here's what a parallelepiped looks like. It looks something like this. You can see that the base of the parallelepiped is a parallelogram. And so really you can think of a parallelepiped as a 3D parallelogram, but what it means for these three vectors to be the adjacent edges of this parallelepiped is that all three of them start at one of the vertices and then reach out to the other three vertices using the edges of the parallelepiped. All right, so here's what I mean by that. If we use this vertex as our starting point, maybe this would be vector v, this is vector u, and this is vector w. This is what it would look like for these three vectors to be the adjacent edges of a parallelepiped. And so by using these three vectors, we can calculate a triple scalar product which will represent the volume of this parallelepiped. And if you want to see why that's true or how that works, be sure to check out my lesson video once again on this topic. I explain it all there. This video, we're just focused on actually calculating the volume and using the triple scalar product. So I'm not going to talk too much more in depth on why this works. Let's just set up our triple scalar product and find the volume of the parallelepiped with these three vectors being adjacent edges. All right, and so here's what that's going to look like. I'm going to take vector v and dot product it with the cross product of vector u and vector w. All right, so we're going to have vector u cross vector w. But now there's actually one more thing that I'm going to add to this expression, and that is absolute value bars. And now the reason I'm adding those is because sometimes the triple scalar product will give you a negative result, but we can't have negative volume, right? We're only going to be interested in the absolute value of this triple scalar product because we're looking for a positive value of volume. All right, and as a result of those absolute value bars, the order in which we perform this triple scalar product to calculate the volume of the parallelepiped suddenly doesn't become all that important. All right, in the previous two examples, I sort of stressed how important it was that for a regular triple scalar product, you wanted to make sure to set up your 3x3 matrix such that this vector's components were in the first row, this vector's components were in the second row, and this vector's components were in the third row. But if you were to swap the order of those rows, the only thing that could happen to the result of the triple scalar product would be that the sign would change, right? If you move around the rows in a matrix, that will just change the value of the determinant by a factor of -1. And so that could change the triple scalar product from being a positive value to a negative value. But since we're calculating volume and we don't care about the sign of the triple scalar product, we just want its absolute value, it doesn't matter what order we put the components of these vectors in our matrix. All right, so when we set up our 3x3 matrix here to calculate the triple scalar product, we could put the components of vector u in the first row or the components of vector w in the first row. It doesn't matter. Okay, so I just wanted to point that out because if you get a problem like this where you want to calculate the triple scalar product of three vectors to find the volume of a parallelepiped, but you're not given an expression like this to know the order of the vectors, instead of getting stuck on what order do I put the vectors in, you can just be at peace and know that it doesn't matter. Okay, so if you ever get a problem like this where the order of that triple scalar product is not given to you and you want to calculate volume, you can set it up in any order that you'd like. But now with that being said, I'm just going to do it the way I have it set up here. I'm going to put the components of vector v in the first row, the components of vector u in the second row, and the components of vector w in the third row. I'm not going to deviate from that setup, but just know that if you wanted to, you could, since we are calculating volume. All right, so let's create our 3x3 matrix here. Let's place the components of vector v, u, and w into this matrix. The components of vector v are 1, 1, and 0, right? We don't have a k term, so the z component must be 0. So we have 1, 1, and 0. Then for vector u, we have no I term, so the x component must be 0, but then we have 1 and 1. So we're looking at 0, 1, and 1. And then for vector w, we have 1 as our x component, but then we don't have a j term, so the y component must be 0, and then we have 1 for the z component. All right, so we have 1, 0, and 1. All right, and so now we have our 3x3 matrix. Now let's find the triple scalar product by calculating the determinant of this matrix. And so let's get started. Let's look at 1 to start, the first value in that first row. We'll cross out the row and the column that it's in and use the remaining 4 values to calculate a 2 by 2 determinant, which we will multiply by 1. We'll have 1 times 1, which is 1, minus 1 times 0, which is 0. So we have 1 minus 0 times 1, that value that we crossed out. Then we will subtract the next term, and for that one we're going to be looking at this one, the second value in this first row, and we're going to cross out that row and the column that that 1 is in, and then use the remaining 4 values to calculate another 2 by 2 determinant. So we'll have 0 times 1, which is 0, minus 1 times 1, which is 1. So we have 0 minus 1 times 1. That would be this one right here that we're multiplying by that 2 by 2 determinant. Then finally, we're going to be adding our last term. However, I'm not going to write it out this time because if you notice, the value that we're looking at in this case, the last value of that third row is 0. We're going to be multiplying 0 by the 2 by 2 determinant that results from the 4 values after we cross out the row and the column that 0 is in. So if we're just going to be multiplying that determinant by 0, we don't really need to write anything out because anything times 0 is 0. So I'm just going to write plus 0. Okay? So that'll save us some time. But then if we simplify, we have 1 minus 0, which is 1, times 1, which is still 1. So this is equal to 1 minus 0 minus 1, which is negative 1, times 1, which is negative 1. So we have 1 minus negative 1, and those two negatives will cancel out. So we'll have 1 plus 1, which is 2. So this is equal to 2. 2 is the volume of this parallelepiped with these 3 vectors as adjacent edges. And in this case, if you wanted to, you could also add on some units to this answer, because remember, this does represent the volume of this parallelepiped, and volume is always measured in cubic units. And so even though we're not told what units we're working with here, we don't have feet, inches, meters, centimeters, millimeters, whatever, we don't know what that is, we can still say that the volume here is 2 cubic units. Okay, and one more thing, I forgot to mention this. We probably should have included our absolute value bars here for this calculation, but since our result was positive 2, that really didn't come into play. If for some reason we did get negative 2, then those absolute value bars would have just made that negative 2 become positive 2. All right, so in this case, the absolute value bars didn't really serve a purpose because we just got 2 as our triple scalar product, but if we did get negative 2, those absolute value bars would have corrected it to be a positive amount of volume. Okay, and so with that, that's it for this example. That's how you use the triple scalar product to calculate the volume of a parallelepiped. And so let's take a look at one more example for this video where we find the volume of a different parallelepiped using the triple scalar product. All right, so here's our last example. We want to find the volume of the parallelepiped below. And so here's our parallelepiped. It has 8 different vertices that are labeled, and we actually have all of the different coordinate points that make up each of those vertices. And what we want to do is calculate the volume of this parallelepiped using vectors, or more specifically, the triple scalar product. Now, we're not told that explicitly in this problem, right? We're just told to find the volume. But since we're in Calculus 3 here, it's assumed that you want to use vectors to do that. Okay, and so in order to do that, when just given a diagram of a parallelepiped, right, we're not actually given the vectors in this case, we're given a diagram with some vertices. What we have to do is find 3 vectors that we can use to calculate the triple scalar product and ultimately the volume. And the way that you want to do that is pick one of these 8 vertices to start with. You just want to pick one vertex and then create 3 vectors from that vertex. All right, and so just to make things simple, I'm going to choose to use vertex A. I'm going to use this point right here to start all 3 of my vectors. We're going to have a vector that connects vertices A and B, a vector that connects vertices A and D, and then a vector that connects vertices A and E. All right, and so those vectors would look like this. This will be the vector AB, so I'll label that as vector AB. Then we'll have this vector right here, which will be vector AD, and then we'll have this vector right here, which will be vector AE. All right, and notice that for all 3 of these vectors that they ride along the edges of the parallelepiped. I recommend that you do that whatever vertex you pick to draw all your vectors from, make sure that the 3 vectors that you draw all ride along the edges of the parallelepiped. Okay, and so now that we've done that, we've chosen our 3 vectors that we're going to use to calculate the volume of this parallelepiped. It's time to actually find those vectors using their initial and terminal points. All right, so here's what we want to find. We want to find vector AB, we want to find vector AD, and we want to find vector AE. And so let's start with vector AB. Remember, if you want to find a vector using 2 points, you want to find that vector in component form, what you have to do is subtract the components of the initial point from the components of the terminal point. So we'll have 1 minus 1, that'll give us 0. And then for the y component, we'll have 8 minus 1, which is 7. And then for the z component, we will have 1 minus 1, which will also give us 0. So that's vector AB. Then for vector AD, let's look at those 2 points. We're going to be subtracting the components of A from the components of D. So we'll have negative 2 minus 1. That will give us negative 3. And then for the y component, we'll have 2 minus 1, which is 1. So I'll write in 1. And then for the z component, we will have 1 minus 1, which will give us 0. So we have negative 3, 1, 0 as the components of vector AD. And then we have vector AE. So we're going to be looking at these 2 points. We'll subtract the coordinates of point A from point E. So we have 3 minus 1 for the x component. That will give us 2. So we have 2. And then for the y component, we'll have 3 minus 1, which is 2 again. So we have 2. And then for the z component, we have 4 minus 1, which is 3. So I'll write in 3. Okay, so those are our 3 vectors, vectors AB, AD, and AE, from this parallelepiped that we will use to calculate its volume. These 3 vectors represent adjacent edges on this parallelepiped. Okay, and so now to calculate the volume, we just need to take the triple scalar product of these 3 vectors, and it doesn't matter what order we do that in. Okay, so I'm just going to do it in the natural order that I see here. I have vector AB written first, so I'm going to dot product that vector by the cross product of these 2 vectors. Again, it doesn't matter what order you choose, because when we are calculating volume using the triple scalar product, we are going to be taking the absolute value of the result from the triple scalar product. All right, so let's set this up. We're going to have vector AB dot the cross product of vector AD and vector AE, and we're going to set up our 3x3 matrix that we will use to calculate the determinant, where vector AB's components will be in the first row, vector AD's components will be in the second row, and vector AE's components will be in the third row. So I'm just going to translate these components right into this matrix right here. Okay, so we'll have 0, 7, 0, and then negative 3, 1, 0, and then 2, 2, 3. All right, now if we calculate the determinant of this 3x3 matrix, we'll start by looking at 0, but now remember, if the value in the first row is 0, you're going to be multiplying that value by the 2x2 determinant that would result from the values after you cross out the row and the column. So since we're multiplying by 0, that's just going to give you 0. We don't even need to write that term. All right, so that first term is just going to be 0, and the same thing's going to happen for that last term. So really all we need to do is look at the middle term, which we get by multiplying 7 by a 2x2 determinant. But remember, we subtract that middle term. And if we cross out the row and the column that 7 is in, then we have these 4 values to work with. So we'll calculate a 2x2 determinant. We'll have negative 3 times 3, which is negative 9, minus 0 times 2, which is 0. So we have negative 9 minus 0 times 7, and then we're adding the last term, which will be 0. Right? Because the next value in that first row is 0, so we're going to be multiplying 0 by the 2x2 determinant using the values left over after we cross out the row and the column that 0 is in. But we don't even need to do that. We're multiplying it by 0, which is going to give us 0. All right, so we don't even need to bother with those 2x2 determinants. We can save ourselves some time by just immediately concluding that those terms will be 0 since we're going to be multiplying them by 0. All right, and now we want to simplify this, but first, don't forget your absolute value bars. And then we have negative 9 minus 0, which is negative 9, times 7 will give us negative 63, but then we're subtracting that negative 63, so that negative will make that negative 63 positive 63. And so we're left with the absolute value of 63, which is just 63. And so 63 is the volume of this parallelepiped that we were given in this problem. And if you wanted to, you could also write down that this is 63 cubic units, all right? Volume is always measured in cubic units, so you can add that on to this answer if you'd like. Okay, and so with that, that is how you calculate the volume of a parallelepiped if you're given its vertices. In this case, we were actually given a diagram showing where all of those vertices are, but if you get a problem like this where you're just given a list of the vertices, all you'd have to do is just work with the first 4 vertices that you're given, make the first one the initial point of all 3 of your vectors, and use the other 3 points after that to make your 3 vectors. Okay, I have an example of that in my lesson video, but I also have another example of that available on my membership site, and so feel free to look into becoming a member if that is something that interests you. But with that, that is it for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.